Okay, so far, we've covered a lot of database and SQL theory, and we've seen how a database can be created. In this section, we'll learn how to assign constraints on tables. This is awesome! We're making excellent progress. Our focus in this lesson will be on the primary key constraint. First and foremost, what do we mean by constraints in an SQL context? Constraints are specific rules or limits that we define in our tables. The role of constraints is to outline the existing relationships between different tables in our database. A few lectures ago, we mentioned that not null is a constraint that can be assigned to a given column of a table. As a matter of fact, we've talked about some other constraints as well. Think about the relational schema of the cell's database. You probably remember what primary, foreign, and unique keys are about, right? They define the relationships between tables and designate whether it is possible to see duplicate values in the same column. In abstract terms, you know how these keys work. To apply them in practice, you must define them in SQL through their respective constraints. Okay. Let's start by focusing on the primary key constraint. We'll work with the same cells table. Here is the code we had earlier. It allows us to create the 4 fields we have in this table. You cannot always apply the auto-increment extra constraint for a given field. To do that, this field must be a primary key, a unique key, or an index. That's why, in this block of code, we have used one possible way to assign the primary key constraint. We have just typed primary key among the constraints relevant to the purchase number column, and everything worked okay. There is another way to do the same job. In that case, we need not mention the name of the constraint in the purchase number row. To assign a primary key, we will have to continue the list of elements within the parentheses. So, I'll place a comma after the constraint of the last field. Then, we will continue on the next line. Pay attention, as this doesn't mean that what I write next will necessarily be a column name. Primary key is a reserved word that allows me to indicate the primary key of this table. In our case, the code we need is primary key, open parentheses, the name of the column, which will be our primary key, purchase number, close parentheses, and eventually the closing parentheses of the create table statement, together with the semicolon. To verify that this works, run the query. If you think you shouldn't do this now because you already created this table in an earlier lecture, please remember that we dropped it at the end, so it will be a brand new cells table in the database. Therefore, to execute the code, press this button with the lightning symbol, or, if you prefer, hold Ctrl, Shift, and then press Enter. Alright, fine. Now, let's prove that we did our job correctly. In the Schemas section in Workbench, after you expand the Tables section of the Cells database, you'll have a list with the tables created. For the moment, you have only Cells. As you hover above its name, 3 tiny icons will appear to the right. Press I, which stands for Info. Does this new window ring a bell? We can get an information window related to our database, remember? This time, only the tabs are different. Info gives you some general data about the table. For instance, Columns offers more information about the column names and the respective data types. It tells you what clauses you may apply to the data in the columns and indicates whether you have added an extra constraint. For instance, here is the auto-increment constraint on the purchase number. Do you see? However, it would be better if you referred to the DDL tab. It is an excerpt of the DDL statement that has been used to create the respective table. So, in a long SQL file, you don't have to go through the entire code to find that particular bit that refers to the creation of the cells table. In the DDL tab, you will always find the information you need. Here, you see purchase number as a primary key. This means we've done our job properly when we added the row indicating the primary key of the sales table. Can you remember the function of a foreign key? It points to a column of another table and thus links the two tables. It is a field or collection of fields from one table called the child table, and it refers to a column in another table called the parent table. Usually, the column or the set of columns in the parent table is the primary key of that table. The child table can also be called the referencing table, and the parent table can be called the referenced table. Good. Now, let's demonstrate how this applies to our database. Shall we connect the cells in the customers tables first? Why not? The primary key of customers is customer ID, and the related foreign key in cells bears the same name. Remember, this is not an obligatory requirement. These two keys may have two completely different names. What's important is that the data types and the information match. It's just common practice to use, if not the same, then similar names for both keys. Okay, great. So, the customers table, the one with the primary key from the relationship, is the parent, or the referenced table, while sales is the child, or the referencing table. Cool! The theory is clear. And how can we establish a relationship between two tables in SQL? Remember the following. A foreign key in SQL is defined through a foreign key constraint. This type of constraint verifies that the values in the child and parent tables match. Technically speaking, we could say the foreign key contributes to or maintains the referential integrity within the database. Good. Let's explore the syntax needed for this operation. Consider the sales table once more. We've already defined all the columns and the primary key. Following the same intuition, we must add a comma and continue with the keyword foreign key, indicating within parentheses the name of the column that will be a foreign key. Unlike with the creation of a primary key, we must not stop here. Let's proceed by typing references, and then indicating the name of the table to which this foreign key refers. In our case, it is customers. Finally, in parentheses, specify the column name, which is the primary key within the parent table, customer ID. In practice, if we leave the closing parentheses and the semicolon at the end, the query will run properly. However, there is a subtlety that professionals regularly add to this line of code. It is the phrase onDelete cascade. What does this mean? Let's analyze it step by step. Cascade means you want a certain phenomenon to affect both dependent objects together and at the same time. This phenomenon is designated by the preceding phrase, onDelete. More precisely, the entire constraint onDelete cascade means that if a specific value from the parent table's primary key has been deleted, all the records from the child table referring to this value will be removed as well. The direction is important, so please pay attention. For instance, if we remove a purchase of customer number 4 from the sales table, we will simply have one less purchase registered in this table, and that will not reflect the customers table. However, if we say Catherine Winfield is not our customer anymore, we'll have to delete customer number 4 from the customers table. Using onDelete cascade affects all dependent objects from the child table, which translates into the loss of the data values of the entire record for purchase numbers 5 and 7 from the sales table. Okay? And this makes sense, right? If we lose a customer, why would the child table need to store a reference to his details when such details don't exist? For this reason, as I already mentioned, Professionals tend to attach the onDelete cascade phrase to the foreign key command. All that's left to do at this point is to run the query, right? Let's check on the outcome. An error. Wow. And why? Let's see. An error message. Table cells already exists. Aha! Right. This is the table we created earlier, and we didn't remove it, remember? We can do three things. We can drop the table and then run this code. If we choose this approach, we will have to add a drop table cells statement on top of this query. Let's execute this entire selection. Bingo! It all worked fine. Now, imagine we're having the cells table registered again without a foreign key assigned. So, we will drop the cells table once more. And then we will create it with a primary key only. Hence, the second viable and much more frequently used option is to add the foreign key by altering the already existing table. As discussed in the DDL statements lecture, the syntax we'll need is alter table cells. And be careful here, don't place a semicolon at the end, since this is not the end of the alter table statement. Write add foreign key. Open parentheses, type the foreign key of cells, customer ID, close parentheses. References customers, which is the name of the referenced or parent table, and then put its primary key within parentheses. As we already discussed, type onDelete cascade at the end to remove dependent objects together if necessary. After we execute this command, we can check the DDL tab of the cells table to verify that a foreign key constraint has been created. The constraint, not the column, was automatically assigned the name cells IBFK1. So, instead of deleting the entire table and recreating it with a primary key only, we can remove the newly created foreign key constraint in the following way. We can type alter table cells, drop foreign key, cells IBFK1, semicolon. Run this query and check the cells DDL tab. Once again, to see that, at this moment, there is no foreign key assigned to this table. Great! Although the focus of this course is on learning SQL by coding, see how the Workbench GUI allows you to add this foreign key, but through the interface without writing code. Right-click on the name of the cells table and select Alter Table. A new window will open on the right side, and you will be able to type the name of the foreign key constraint, which, pay attention, need not coincide with the name of the column. This is just an option for naming the constraint, not renaming the column. Then, you could pick the referenced parent table from a list. Here's the moment to designate the column to be a foreign key and the referenced column. Finally, onDelete cascade can be added from this little list on the right side of the screen. Great! As we press the Apply button, which is located over here, we'll add a foreign key to the cells table. To verify that this happened, look for more information about the cells table. If you check the DDL tab, you'll see that customer ID has been mentioned as a key, more specifically, a foreign key. In addition, if you prefer, there is a Foreign Keys tab, which contains a list of the foreign keys assigned to this table. On the right side, you can see which is the referenced column, customer ID, as well as the name of the table to which it refers. This is the referenced or parent table, customers. Okay, let's recall what unique keys are about. They ensure that all values in a column or a set of columns are different. Just like primary and foreign keys, unique keys are implemented in SQL through a constraint, the unique constraint. Each data value of a column that has the unique constraint is intended to be unique across an entire column or set of columns. Therefore, if you attempt to insert an already existing duplicate value in the unique column, SQL will display an error. Consider the customers table from the sales database. Earlier in the course, we said that the email address field is unique because it is impossible to have two identical email addresses. The syntax to abide by is analogical to the one we used when assigning primary or foreign key constraints. Therefore, we have to attach the keyword unique key to the query we created earlier, and that's it. By opening the DDL tab of the Customers table, we can verify we have applied the unique key constraint to the email address field. Fantastic! Now, we will drop the table, and then we will recreate it without setting a unique key. Okay, done. There's another way to add this constraint. Given that the customers table has already been created, the unique key constraint can be added through the alter table statement. Therefore, type alter table customers, and then, for better legibility, preferably on a new line, write add unique key and email underscore address in parentheses. Finalize it with a semicolon at the end. Now you can run this query. Okay. At this point, we can check the DDL tab of the information section of the Customers table. Yes, the unique key constraint is applied. Awesome! Here's the right moment to introduce indexes. We've left the detailed presentation of this topic for much later in the course. The reason we approach it now is because unique keys in MySQL have the same role as indexes. However, remember that the reverse isn't true. Think of an index of a table as an organizational unit that helps retrieve data more easily. This also means that records in a table can be accessed more quickly. Of course, this doesn't come without a cost. It takes more time to update a table because indexes must be updated too. And that's time-consuming. As a result, think of an index as a MySQL tool that can be created in a column, which will be frequently used to retrieve information from a table. Hence, the automatic treatment of a unique key as an index in MySQL. So, if we want to remove a unique key from a table, we must use the following syntax. Alter table, table name, drop index, and not drop unique key. Name of the unique key field without parentheses. To apply this syntax to our ongoing exercise, let's drop the unique key constraint implemented to the email address column. Write alter table customers and then drop index. Email underscore address. I'd like to remind you once more not to use parentheses here, as this is the relevant syntax for the drop statement. Right. Execute. Now, let's check the DDL tab for the Customers table once more. Here we are. No unique key constraint visible. Wonderful. You will see it in almost all databases you will work with. It helps us assign a particular default value to every row of a column. A value different from the default can be stored in a field where the default constraint has been applied, only if specifically indicated. A good example is the number of complaints column in our customers table. It is reasonable to think every new customer has submitted 0 complaints at the moment of registration, right? Hence, it is logical to set the number 0 as the default value of this field. Theoretically, in a create statement, when creating the customers table, the default constraint could be easily added at the end of the row referring to the number of complaints field. After specifying the name of the column and its data type, integer, we must indicate the constraint default. What follows must be the default value we want to assign, complying with the data type set. In our case, we must set 0, surrounded by quotes, or even without. For MySQL, in this situation, using single quotes, double quotes, or no quotes will be the same. As an exercise, you can drop the customers table and recreate it by setting the default constraint to the number of complaints field. This constraint could be added through an alter statement, and that's the model we'll apply. We can start altering the customers table in the well-known way. After that, we should add the change command, column, then indicate the name of the column to be changed. Repeat its name, unless you want to change the name too. Then, we must specify the data type and write default 0. Finally, remember we developed the good habit of placing a semicolon at the end of every statement? Let's do that here too. Now, we can run this query and done! Let's check if the default values were applied properly. For this task, we must insert a new record, deliberately leaving the number of complaints column with no value. We'll see if a 0 will appear there automatically. It will be sufficient to add a first name, as we declared it cannot be null, a last name, and a gender, for instance. The customer ID increments automatically, so it is supposed to augment by 1. We do not have to add the email field, so we can just skip it. Let's improvise with Peter Figaro, male. As we run the query, this record will be added to the customers table. To prove this, we can make a check by selecting the list of all records in the customers table. Type select star from customers, and you will obtain a full picture of this table. Bingo! 2 was automatically assigned as a customer ID. Had you inserted more than one customer in the table, this number would have been equal to the next auto-increment value. Peter Figaro, male, appears. The email is shown as null, as we indicated no value for this field in this row, and 0 was put in the number of complaints column directly. Amazing! Setting a default value works. Instead of adding an entire record, you could have verified that the default constraint was set correctly by checking the DDL tab. Let's do this. And no surprise, we see default 0 over here. Therefore, it appears the DDL tab can always tell us if we have implemented a constraint properly, right? Finally, don't be shocked by the fact that the default constraint can be dropped as well. Alter the customers table. Then change the respective column, which is number of complaints, by dropping default. This time, I will not remind you to add the statement terminator at the end. Check the DDL tab and do we see a default constraint there? No, we don't. This means we have removed it successfully. Perfect! When we introduced primary and unique keys, we discussed the main difference between the two. In a primary key field, all your values must be unique, and you may not have null values. In a unique key column, all your values must be unique, but it is unnecessary to have data in all records. This means you can have null values. The not null restriction is applied through the not null constraint. It means that when you insert values in the table, you cannot leave the respective field empty. And if you leave it empty, MySQL will signal an error. In our case, the idea is to keep company details in the companies table. We can see the three columns of the table: company ID, company name, and headquarters phone number. What we will do now is add the not null constraint next to the company name column and see how this changes the functionality of this table. Okay, let's deal with the syntax for creating the companies table. The company ID column is the primary key. Each company ID is associated with a company name and a headquarters phone number. It is fine if a phone number is not provided. The information not to be omitted here is company name. Therefore, when creating this table, after the row corresponding to this column, we must specify the data type, which is varchar 255. Then add the not null constraint. By doing this, we ensure there will be no missing data in the company name column. We did not use the maximal length of the varchar data type. Drawing on my professional experience, we don't need the maximal varchar length every time. To improve performance, we could use the shorter length of varchar 255. It would suffice, and that's why we'll use this value here. Excellent! This time, we'll not even go to the DDL tab of the companies table to check we applied the not null constraint successfully. But it would be a wonderful idea for you to do this as an exercise. Let's drop the not null constraint through the alter table statement. The syntax that will allow us to do that is specific for the not null constraint. This time, we shouldn't combine alter table with alter column, because we won't drop the not null constraint. In MySQL, we must modify the constraint to go back to null. So, the code we need is alter table companies, modify company name, varchar of 255 null. Execute it. And if we check the DDL tab, you'll see that a not null constraint has not been indicated next to the company name field. Otherwise, we could attach the not null constraint through the alter statement. Alter table companies, then change column, column's name, repeat the column's name and data type, and then type not null. So, when you run the query and check our favorite DDL tab, you can see a not null constraint has been added. Bingo! If we try to insert a row with data where we provide no company name information, we should expect an error message from MySQL. Let's see if that's true. I'll insert just a headquarters phone number because company ID will be automatically incremented, and we want to leave company name empty deliberately. We'll improvise with a random phone number, written within parentheses and within single quotes, as it is a string value. SQL gives us an error stating field company name does not have a default value. This means we have neither set a default value for the company name column, nor have we assigned a company name value to this record manually. If you wonder what the error encountered is, you can hover your mouse over the message field corresponding to it. A little box stating the issue will appear, and you will know precisely what went wrong and what needs to be corrected. This is how the not null constraint came into play. MySQL gave us notice we must insert a data value in the company name field. Great! Let's correct our mistake. Now, we will insert a company name too. Let's say it is Company A. When you rerun the query, you won't see an error appear in the lower section of the workbench. And as we select all rows and columns from companies, we see our new entry is there. Company A with its headquarters phone number. Please don't confuse a null value with the value of 0 or with the non-response. Instead, think of a null value as a missing value. 0 or non could be values assigned by the user, while null is a value assigned by the computer if the user has provided no value for a given record. If you know John McKinley has filed 0 complaints, then in the number of complaints column in the customer's table, you could insert 0. This does not mean the value is null. Not at all. You have a value, the value of 0, and the information in this field for the first record is not null. It means John has filed no complaints. If we have no information regarding the number of complaints John has filed, then the value would have been null. By the same logic, imagine there was an additional column called feedback, and that it is optional. Had the first 3 customers provided some feedback, while Catherine had said she did not want to leave any, does that mean this value is null? No, because Catherine said she did not want to provide any feedback, so we could mark her response as none. Had she not replied yet, only then our value would have been null. Fantastic!